So I wanted to start with just a couple of corrections from the slides from last time. So this code, I can't edit it easily because it's an image, but this section at the bottom, while not our task dot next dot compare and set with null and our task, this our task should be done, the done task. So this X task and the diagrams preceding this, that's the, yeah.
Refresh your slides. I just put a better one in on slide 35. So if you refresh and go to slide 35.
Oh, but it's not, it doesn't have colors.
I'm sorry.
How are we supposed to read this without colors? Okay, well, yes, here is a corrected version of that code we just saw. So now we can see, and I can actually show you the guard code in a moment here from the repo itself, but yeah,
But this is going to be less cluttered, simpler.
yeah. Do we have any questions about this code from last time or new ones now? Okay, I will take them as they come. The other very important thing is that these graphs, lower is better on these graphs because the y-axis is the runtime in milliseconds of each benchmark. I had to take those labels out of the slide to make them legible at a distance, but yeah, so in this set of graphs, locks and guards are very comparable. Reentrant lock is very slightly better on Intel in this particular benchmark, but here on Intel and AMD, guards are actually a fair bit better than reentrant lock. And then RISC-V, they're a bit worse. And they're quite similar on this benchmark as well. The accumulator benchmark on Intel and AMD guards are a hair faster. On RISC-V, they are a thicker hair faster. And ARM, it's kind of hard to tell because there are so few cores, but anyway, I think that's all we had to address about the slides, right? Okay. So the heat equation. So we talked about, yeah.
Explain like is okay, so I'm guessing the x-axis is the amount of threads.
Yeah, so the x-axis is the number of threads, yeah. Yeah. So
Why are there so many dots here? Like are these just like
so we run the benchmark multiple times per number of cores to account for error, right? Because there can be noise in the system and other factors that make the result skew one way or the other. And if you run a lot of them, you can average it out and get a typical runtime instead of risking, if we only run it one time, we might end up with this data point up here that's way higher than the rest. Yeah. What's your name, Reagan?
Like what situation is this better?
When you want to use locks, but you want to have no risk of creating a deadlock or a race condition bug. So the main advantage of guards is that they are safe, and you can't.
Find the wrong situation. So why would you put this over there?
I'm not. What situation would that be?
Trying to implement something. Probably find a lock that would work and wouldn't deadlock in a specific situation.
No. Locks are the problems with locks and composability are generic
Yeah.
for locks.
Locks always, when you do a locking operation, you're always going to block, and that blocking creates non-composability problems just because of the properties of locks. If you change those properties so that it doesn't have those problems, then what you have is something that isn't a lock anymore. Does that answer your question?
Which code?
Yeah, which code?
You remember what it was a code of?
Okay.
I can see it on like the code part of.
Oh, yeah, it's not uploaded. Okay, so we did 3 bank problems. And we did read-only part list. We did the read-write guard.
I think that's the only place you know.
Okay, there's the read-write guard. The code should be there.
Yeah.
There it is. Okay, I wrote this code. Max may not be as intimately familiar with it as me, so we'll see how you do with reading my code on the fly.
Well, is there any part of it that you wanted to go over, or do you want to just go from the top? All right. Maybe you should talk about it because I haven't written this or read it.
Yeah, I can do that.
Just for the sake of your brains. Yeah.
They can plan, for the sake of sanity and clarity, this will no longer be in Polish, but will be in English for the rest of the movie. This is there's this movie To Be or Not to Be with Mel Brooks, and they start off in Polish, and then this announcer says that, and they switch to English. It's a good movie, actually. All right. So the read write guard is a kind of like the read write lock in the sense that we build it out of existing things. We build it out of guards and condition variables for guards. Um, and uh, so you scroll the opposite way as me. Great.
Scroll the correct way.
Okay, so this thing has a guard and it has a condition variable. And when you construct it, there's a parameter called balance, and that's roughly the number of reads per write that you expect that you think is ideal. Um, and it has a couple of fields it uses. It uses a read count, and that's the number of threads that are currently reading. And then there's a write waiting, which is the number of threads that want to write but haven't started yet. And then there's a read waiting, which is the number of threads that want to read but haven't started yet. And there's this Boolean called writer's turn, and it returns true if the number of writers waiting times the balance is greater than the numbers of readers waiting. So the run read method is going to has got two arguments. Let's scroll down. So if I want to call run read guarded, so I want to call a method and I want it to have read access to this guard. I pass it this runnable method that I want to run in that critical section. And then I call run condition and I create a new condition variable. And so I'm using this capability of Java anonymous inner classes where I give the class a field. And then the field is anchor waiting, and it's just a piece of state. And it's going to be true the first time this check method is called, and then false ever after, right? So that's how I do this. So because run read is going to run multiple times in the condition, right? But I need to increment the waiting variable only the first time, right? So I use this little bit of state to help me keep track of that. So I say anchor waiting equals this Boolean here, and then I set anchor waiting to false, and I pass it as the second argument to run read. And I do the same trick on the write method. So each time I'm able to do the increment the reader or the writer waiting only once, and that's the first time the method is called. But as you know, because it's a condition variable, this run method has to run multiple times until it returns true. Okay, so if I go into the run read, if it's the first time I call the anchor waiting, right? And then if it's the writer's turn, I return false. And if it's not the writer's turn, then I can read. So I'm going to decrement read waiting. I'm going to increment read count. I'm going to create a completable future, which I think I don't use, and I think I should just delete from the code. And then what I'm going to do is I'm going to submit this run method to the pool to run. And then when it finishes, it's going to have there's a future on pool run, and we call then run, and it's going to get the guard on this method, decrement the read count, and signal all. Okay, so that's how the read works. Got it? Okay. And I'm always going to scroll the wrong way. And then run write is simpler, right? So first time I increment the waiting. If the read count is greater than 0, or it's not the writer's turn, then I return false. Otherwise, I call run me, which is just going to run the method directly. And then I'm going to decrement the write waiting count, signal all, and return true. Okay. And this combination of things lets me do a read write on this guard. And there's a test for it somewhere. No, I can find it. It's test read write guard. right? So I just have I have a unit of artificial work, which is just sleeping for some random amount of time. And yeah, and then inside the loop, I ensure that assertions are enabled. And then I have a run write guard and a run read guard. So I have this this parallel for loop. So I'd forgotten I introduced this concept. So that we have this thing called a loop.power4, and that's going to be kind of like a loop, but each element, each it's going to have a beginning and an end for the loop, like you would with a for. And the body of the loop is going to be a lambda function. And in this case, the argument to the lambda function is the loop iteration. So this J will go from 0 to loop count -1. And each of these methods will be called in a new thread. Okay. And what it's going to do is if J is even, it's going to call a write guard. And if it's, oh, I'm sorry, if J percent write every is even, is 0, then it's going to call a write guard, and otherwise it's going to call a read guard. So it's going to call read guard more frequently. And when it calls the write guard, it's going to print write, artificial work, writer count, plus plus. And if it does the reader, it's going to do a reader count, increment, and get. And then in either case, it's going to complete a future to signify that it's done. And the way a power4 works is each iteration of the loop has to return a future. And the system is going to collect all those futures. And when they're all done, it's going to be done. So I put a join at the end of this power4. Questions? Yes, McKay. Okay. Correct. There's no, so the question was, there's no read and write threads, there's just read or write tasks, and that's correct. Reagan. Yes, I can. I just have to use somebody else's computer. Yeah, there's run guarded.
Is it kind of like no.
Yes, it's kind of like a monitor, but not really. It's the guard equivalent of a monitor. Like, that doesn't sound too good. It does sound like a disease. It sounds like a C++ STD disease. Anyway, yes. Yes.
Is that just kind of like kind of arbitrary?
Yes. Yeah, it's just so what's going to happen is if I queue up a bunch of things dynamically, right? It might be that hundreds of them queue up before any of them execute. And in that circumstance, it's going to try to maintain a balance between readers and writers. Are we good? Back. Yes.
Slide 35 where you just put the code up. and
Yes.
Run through it.
I'll let Max do that.
Okay.
Yes.
So yeah, so we have a class guard and a class guard task. And guard is going to have a next field. It's going to have an atomic reference to a guard task. This is just going to represent whatever task is running next. And then here's run guarded. It takes a runnable R. We're just going to construct a new guard task, which wraps around the runnable, right? Guard task is just a way for us to add extra functionality to a runnable, right? Because runnable is already a standard thing in Java. Then we grab the task that used to be in the next field. So we do get and set with new task. That will do an atomic exchange. It'll put new task into the next field and return out whatever was there. And then we check it against null. And if it is null, that means there was no task enqueued on the guard. And so we can just go ahead and run the new task directly. Otherwise, if we did get a task back from the next field, we then try to compare and set from null to new task on the next field of the task that we got back. And if that fails, that means that rather than null being there, done was there. And if done was there, that means that there's also no currently running task, and then we can go ahead and run the new task directly. again. But if this does succeed, then we don't have to do anything else because what we've done is we've put the new task on the next field of the old task. And so somebody else will come along later and run this task for us. Right. And then in the guard task, we just have a reference to the critical section. So it's a runnable. We have the next field of the guard task. We have just the static done task because we compare it by equality, a reference equality. We have a constructor, which just takes the runnable and sets critical section to be equal to it. And then we have running clean, which just runs the critical section directly. And then we have a variable that points called our task that currently points to us. And we're going to march through the next pointer of our task. We're going to look at our next field and try to put done there if null is currently there. And we keep marching through the next pointers until we reach the end and until we can succeed in putting done there. And once we've done that, we're done. So the body of this while loop is essentially, this is the case where you have a bunch of tasks that have put themselves into the next field at this point. So we just run through all the tasks that are in that chain until we reach the end, and then we put done there. Do you have any questions about that?
I don't think so.
All right. So now I would like to move on to the heat equation. So I'll start from the top on this. The heat equation is going to be a partial differential equation which describes the propagation of heat through a medium. So for this class, we're going to implement it in 1D with periodic boundary conditions. So you can imagine this like we have a limp noodle of spaghetti whose ends are joined, and we're simulating the propagation of heat through that spaghetti noodle. So the 1D heat equation is given.
Shoot, you didn't start the Zoom the right way.
Oh, what's the right way to do it?
Start from my Zoom room, because Farron can't join. Can you get me a Zoom link and I'll put it in Discord?
Okay.
I don't know if you can or not. I've never done this. I don't know how you do it.
I don't either. Should I just end the meeting and join your room?
There a share somewhere? I don't see it.
Share link. Participants.
Yeah, we can buy it.
Right.
And then click on
Uh-huh.
Right? You can paste that to me in Telegram and I'll put it in Discord. And if anybody has a way to get a message to Barrett, I'll check in Discord.
Okay, is it still recording? Yes, it is. Okay. So, right. So we have a partial differential equation here. So we're saying the partial derivative with respect to T of U, where U is the temperature, is equal to alpha, which is
Yeah, okay, sorry about that.
which is a thermal diffusivity constant times the partial second derivative with respect to X of U. So remember, U is the temperature, A is just some constant representing how well the thermal energy propagates. T is our time coordinate and X is our spatial coordinate, right? So the way we do things numerically is we have something at one slice of time, and then we step through progressive time steps, right? We evolve it one step forward and then one step forward again and again and again until we get to where we want. So we're always going to be adding one or adding 1 times dt to this time coordinate every time we step forward in time. Does that make sense? So to implement this numerically, we need to discretize the equation in time and space. So the first step is we need to write our derivative as a finite difference, which there's a link here if you want to read more about that on Wikipedia. Yes.
this size.
So we have this, the way this is written, this is a continuous equation, right? But on a computer, we don't have infinite space. So we need to somehow discretize it, meaning we need to cut our space up into discrete pieces and cut our the continuum of time into distinct steps. That's all we're doing, right? We're turning it into a problem where we can add one to the time coordinate and the space coordinate instead of having to, compute the right, because in continuous space, X can be you can infinitely subdivide a number and get infinitely more decimal numbers, right? If you have a continuous coordinate system, there are infinitely many numbers between 0 and 1. Whereas on the computer, we can't represent that. So we need to have a fixed number of numbers between 0 and 1. Yeah. So in other words, given some value of u at some time coordinate and space coordinate, we want to know how to evolve that to the value of u at that same space coordinate, but at the next time step, where dt is the time step size. So to do this, we're going to have a Taylor series expansion. So we want to write u of t plus dt and x like this, where we start at u tx because that's what's known. And then I don't know if you know what a Taylor series is, but basically it's a formula you can apply, right? We're just doing this to this symbol, and that results in this infinite sum. We can do a trick where we assume that dt is infinitesimally small and therefore neglect terms of dt where we're raising it to a power of 2 or higher. It's just so small, it's not even worth thinking about. So we can chop off everything to the right here, and we end up with this, where u of t plus dt and x is approximately equal to u of t and x plus dt times the partial derivative with respect to t at the current time and space value. So this is basically Euler's method. I don't know. Are you familiar with Euler's method? Yeah. So we can extrapolate the value of a function by just taking its derivative at some point and then multiplying that by dt. So isn't this the same as this?
No, it's the X instead of.
Oh, right. Okay. So here we have another Taylor series, but this time we're evaluating at x, and we get a similar looking thing. We're going to do a few tricks here. So this is the Taylor series evaluated where we are extrapolating, we're adding dx rather to x, and then here's the same thing, but we're subtracting dx from x. And we can rewrite this one slightly differently to make them easier to add, and then we add them together, and we can do the trick just to get some value. It'll make more sense in a bit.
If you add them together, it gets rid of the first derivative, because we're trying to get at the second derivative. So if you add them together, it gets rid of the first one. Go ahead.
Yeah. So we do the same trick where we chop off the end, and then we want the x derivative, right? Because we need the t derivative and the x derivative both. So
The second X derivative.
yeah. So if we solve for that, we come out with this, where we say the second x derivative of u is this thing. And you can see that the right-hand side is all in terms of values of u that are at the same time coordinate that we are currently at, which means all we need to extrapolate the next time coordinate, or the value at the next time coordinate rather, is values at the current time coordinate. So now that we have this, we have all the tools we need to simulate the heat equation on the computer. So to discretize in space, we just pick the size of a grid, and we pick how far apart the grid points are from each other. So we pick an n and a dx, and we're just saying that we have the set of grid points x, and the grid point x sub I is the ith grid point, which corresponds to the spatial coordinate at I times dx, dx being the grid spacing. To discretize in time, we use Euler's method and this second order derivative we derived earlier to get this expression. And we have a bunch of terms here, dt, a, and dx squared, that we want to factor out into one term c, which whoa, that's not, what in the world? Okay. So we have C, and for numerical reasons, we want to fix C at 0.49 because if we don't do this, then we'll have floating point round off inaccuracy errors. So this, for our purposes, this will decide a delta t for us after we have chosen a dx and an alpha. So this here, this expression is a basic stencil function or a kernel function. To compute the value of any particular grid point at any particular time step, we need to be able to read the values of that grid point at and its neighbors at the previous time step, right? Because you can see the thing we're multiplying by C here, we have to read the current time step, but our left neighbor, right? It's the I minus 1th grid point. And over here we have the same, we have the right neighbor. So let's say we have an array of values representing our noodle. We have 5 whole grid points. It's a very coarse noodle. So to evolve this noodle one step forward, we have to calculate one grid point at a time according to the stencil that we've made. And then we store the result in a new array. And then we keep doing that again and again and again. So you can imagine the array that we're, yes. Yeah. So it's just an array, basically. So you can imagine, yes. To simulate the propagation of heat through a spaghetti noodle. Why wouldn't you?
So there are countless physical systems that you want to simulate on a computer, storm surge, black hole collisions. And this code is essentially just like all those other things except greatly simplified. So the heat equation is the simplest time code of that genre that you can possibly write. And so that's the exemplar. No, not for the quiz. You will need it for the final.
I sure hope
Good question.
Yeah.
Real
I believe that the value of 4 and 1 calculated out.
I'm sorry, what?
When you get the value of the next one.
Well, you don't. The next time step is the one you're trying to calculate. So, right. So these, well, you have some initial data, right? You have the noodle at some initial state that you're starting from. So you just choose values. Well, then your simulation's wrong.
Hey, so can I take a stab at something real quick?
Well, just don't do that. Right? I mean, if you're trying to simulate some specific evolution of the noodle, you have to presume that you know how the noodle starts. If you don't know where you start from, then there's no hope for you. For a more complex problem, say we're trying to do something a little more complicated than a spaghetti noodle, like, I don't know, a black hole. Figuring out the initial conditions for space-time with a black hole is actually an entire field of problems by itself. And we have like black hole initial condition solvers that try to solve equations to get the initial conditions, and then we solve more equations to evolve those conditions. So it can be not straightforward, or it can be as straightforward as, let's just say we have a noodle whose end is hotter than the other end, which is what we're doing in this example. So like here, you see, I've just set the values manually, right? 1, 2, 3, 4, 5. And for our purposes, that's a good starting point. Anyway, so the
Hello?
time step that we're starting from, you can imagine, as we're trying to compute the next time step, we have a sliding window that shifts along this noodle, where the middle cell is the one that we're
I want to be
trying
adult.
to compute the next time step of, but we also need the left and right neighbors, right? So even though we're computing one value, we need to read 3 values, and they're all neighbors.
But if you need the previous values to get to the next values, then how are you calculating the next value? That you need to find out.
By evaluating this, right? So this thing on the left-hand side, that is the value of u at some coordinate xi at the next time step, right? And so this right here is the current value, right? So we have that, we're given, because this is where we're going from. And if this happens to be the first time step, then we've set those initial data ourselves, right? And these are all the same time step that we're evolving from, not to. The difference is the space coordinate, right? We're not looking backward or forward in time, we're looking left and right in space. Does that make sense? So the x coordinate is space, right? Negative x is to my left, positive x is to my right. The time coordinate is what happens later and before, right? We're always going one time step forward. We never have to get times values of future time steps to compute values in this particular problem. It might make a little more sense after I talk a little more. So given we have this, right, this is the state of our noodle to start with. Let's say we want to compute the value at the next time step for slot 2. So by using this formula, we come up with this, right? The next step at 2 is the previous step at 2 plus c times this function of the neighbors. Right? Does that make sense? So for the rest of the interior, we can generalize it like this, right? It's so in the square brackets here, the way we've modeled it is that this is the space coordinate. So 1 is the left neighbor of 2, and 3 is the right neighbor of 2.
I'm gonna put this page he's working for out from, I'm gonna put the link into the Discord.
Yeah. So basically, the main takeaway you want is this equation here, right? You can just sort of take this equation as a given. This is how you discretely evolve the noodle in time, and then you just apply that function to your data in parallel. Right? If you understand how to do this computation, you don't have to get here. You just know how to take this and do it, right? Like, does this make sense? Are you convinced that this depiction right here models what we've written up here? Yeah. Are we all convinced? How about you, Reagan? Okay. Well, okay. So look, so next step and prev step, right? You can imagine prev step is just at time t, and next step is at time t plus dt, right? Is that okay? And this is an array, right? So next step and previous step are arrays. Previous step holds all of the data points at some time for all the x coordinates. And next step is the same, but for the next time step, it's all the x values. And, well, y values at coordinate x. And so, right, this is the current one, right? So these two are at the same space, but this is the current step and this is the next step, right? This is the current step. This is the current step. This is the next step. You see that connection? Now, here we're just saying these three are at the same spatial coordinate as this one, at the same time coordinate as this one, rather, at different spatial coordinates. So this one in the middle that we're multiplying by -2, that's actually just the same as this one on the left, right? You can see that? Reagan? Okay. This symbol, UTXI, is the same symbol as right here, right? So U is like a big 2D array, you can imagine, where the rows are indexed by this bottom coordinate and the columns are indexed by T, right? Where T is time. Because we want to have a copy of the noodle at every point in time. Right? So we're saying here we need to look at our neighbor on the left at the current time and then subtract from that 2 times the value of ourselves plus the value of our right neighbor. That's all we're saying here. Does that help? Okay. In which way does it not help? It'll have to come out. Well, I would like to help you understand. Can you try and explain what part of this you're not understanding?
I don't have to really go back and look at it. Take a couple hours and stare at it.
Okay. Well, you might have to stare at it. That's fine. That is frequently the case with these things. You just have to stare at it. Yeah, look, it's okay. But you do understand this, right? You understand, right? To get to the next step, we just apply this function to three values. And those three values are ourselves, our neighbor on the left, and our neighbor on the right. Okay. And so at the boundaries, we have a problem, right? Because at index 0, we don't have a left neighbor. We have -1, which is out of bounds. And the same goes for 4. Our right neighbor is out of bounds because 4 is the highest index we're allowed. But in this case, as we said, we were going to use periodic boundary conditions, which means that the left neighbor of 0 is just the rightmost element, right? Because the ends of the noodle are attached. It's a circle. So in this case, to compute the next step at 0, we just wrap around and say our left neighbor is previous step at 4. And we do the same thing for next step of 4. Our right neighbor is previous step at 0. Are you okay with that? Are we happy? Okay, there are no complaints, so we're all happy. So the standard way to parallel, so you can imagine in serial, the way you would do this is you would just march through the array. Like, okay, next step at 0, it's this. Next step at 1, it's this. Next step at 2, it's this. To parallelize it, you would just split up this array into chunks and let every thread do that same procedure on the chunk of the array that it's allowed to access. Right? So we split the array into chunks, we pass each chunk into a different thread, and then allow each thread to evolve its own chunk in parallel. However, the fact that we need to read from the point's neighbors introduces a problem, because say we're evolving the leftmost grid point in a chunk, and then another thread has to own that left neighbor because it's in a different chunk. So we can't actually access it without some kind of synchronization. So illustrated, here's a little diagram. Let's say we have 10 grid points and we've split it up between two threads. Thread 1 is responsible for evolving these points in time, and thread 2 is going to evolve these points in time. But let's say thread 2 wants to evolve 0.5, it has to read 0.4, but thread 1 owns that point. So there's some synchronization needed. We need a lock or something. Or in this case, we need a guard. So the solution for this is what's called ghost zones. So these are extra slots in the array that serve to hold copies of values which need to cross those thread boundaries. And in between time steps, we have to synchronize or update those ghost zones so that each thread has a current view of those values that are at its boundaries. So here's an example of this, but with ghost zones, right? We have extra, so in thread 2, all the way on the left, we have a copy of this value. And at the end over here, we have a copy of this value. And then in between time steps, each thread just sends the values to each other. Yes, the spaghetti noodle is a donut because we have periodic boundary conditions. We have joined the two ends of the noodle together. It's a spaghetti-o.
I think you saw the same exact thing with Lucas when he talked about MPI memory. Routine of life.
Yeah, so this is, if you're using distributed memory, as you heard from Lucas, when you're doing MPI, that's distributed memory. So you have multiple machines with their own RAM that can't talk to each, there's no shared memory, it's distributed. So the threads have to talk to each other because those two threads might be on different machines. And so you have to actually pass messages around to send the values into the ghost zones. But with guards, we're working with shared memory, which means that we can eliminate ghost zones if we're very careful about how we synchronize, right? If we can just read the other thread's values, then so long as we're synchronizing correctly, we don't have to send messages around necessarily. And Guardian supports this, but for this particular problem, the most straightforward way to do it is where we have a mixed scheme where the boundaries are implemented with ghost zones, but the neighbors on the interior are just this shared memory solution where you're just reading your neighbors with synchronization. So with guards, this is what we end up with, right? On the very left, we have a copy of the value on the very right, and on the very right, we have a copy of the value on the very left. But in the boundary here, thread 1 is just allowed to go over here and look at its neighbor's value, but we still need synchronization to do that. Are we okay with the heat equation? Are there any questions? We're going to look at the code after this, so yes.
What about, it's how to, exam? I guess that's synchronization, so.
It's just the fact that we're running on shared memory. Because we have shared memory, then every thread can actually read every other thread's memory. The question is, can you do it safely? So you still have to synchronize when you do that. Does that make sense? Any more questions before we look at the code? Okay, let's look at the code. So here is the plain guards in Java heat equation. So there's a lot of nesting here, so it can be a little hard to read. So feel free to stop me and yell questions at me. Okay, let's make it bigger. Let's figure out how to make it bigger. No. Too easy. That would be too simple. Alt Shift period, naturally. Oh, yeah, Alt Shift period did it. Is that big enough? Okay. So, okay. First we have some, geez. First we have some constants. We have the number of threads we're going to use. We have the number of iterations we're going to use. We have the diffusion constant, so that's alpha from before. N is the size of the grid. This is just setting up dx and dt because remember we wanted c to be this value, so we're just solving for dt given a set dx and alpha. So what we're going to do is we're going to make a list of two partitionable lists of doubles. So what's partitionable lists? So this is a class that we have in guards in Java Linear, which is a fixed size mutable list with machinery for splitting up work between different threads. So the work of partitioning an array and sending it to different threads and having them do stuff and then collecting the values again at the end, partitionable list handles all that for you. So we want two of them because we want to be able to ping pong between which list we're reading from and writing to, right? So when we start, we're going to have all our data in the first list, and we're going to read from that and write into the second list. And then the next time step, we're going to read from the list we just wrote to and write back to the first list. We're going to back and forth like that. That's why we want two of them. So Y is going to be our list of those two part lists. So this call to Y add is just constructing a new part list with our initial data. This is, I guess, some kind of Gaussian curve. I don't know. Do you remember what this does?
Gives it a random time to put time.
Well, it's not random. It's
Well,
it's some curve.
Yeah, it's like a guess.
Yeah. And the second list is just going to have nothing in it because we're writing to it. We're going to overwrite whatever we initialize it to. And then we have marching 4. So par 4, remember, is we run the loop body, n times all at once in parallel. Marching 4 is different. Marching 4 is going to run the loop body in sequence. So it's going to run the 0th iteration, wait for it to finish, and then run the first one, and then the second one, and then the third one up until n. And it's going to return a future that reflects when it's done. And that allows us to basically, because the reason we want marching 4 here is because the body of the loop is going to do stuff that returns futures. And so we don't want the next sequence of operations to start until after we've evolved one time step. So inside the body here, we're going to construct a future that will be the thing that we use to signal to marching 4 that one loop iteration is finished. You can see at the end, we return that future. That's a very common pattern. We're going to call run partitioned, and this is going to be the thing that does our work in parallel. So we pass to it the number of chunks we want to use. In this case, that's the number of threads, right? We have 2 threads, so we want 2 chunks. We pass the number of ghost zones, and this is the number of ghost zones on each side. So remember, we need 3 different values. We need ourselves, our left neighbor, and our right neighbor. So that's 1 ghost zone on either side of us. So we pass 1 here. Next, we pass a list of part intents. So this is going to tell part list which part lists, or sorry, this is going to tell run partitioned which part lists that we're reading from, writing to, and which ones we need read and write access to. And this is important because with ghost zones, you don't want to have overlapping write and read regions, or else you get race conditions. So we say we want to read from the first list and write to the second one. Right. And then finally, we pass it a lambda, and this lambda's parameters are going to be views into the lists that we've passed here, right? So we say we want to read from the first list and write to the second one. These parameters are going to be a read-only view and a write-only view, because that's what we've said over here. Are we good on that? Are we happy with that? So in the body of the first run partition call, you're just going to calculate C, and then we're going to iterate over the view. This is just a normal for loop. We're going to go from 0 to writable size of the writable view. And at each grid point, we're going to set the value at that space coordinate I to this expression, which is just the expression we figured out before, right, in terms of the neighbors. It just looks ugly because there are calls to get and set. And then run partition is going to return a future. So once all of the chunks have had all of this work completed, then this future completes. And then we can do dot in accept, which tells Java, hey, I have a task for you. Run it once this future is completed. So we're going to say, once this run partition is done, we're going to do another call to run partition. This time we only want one chunk and we want read-write access. So we're just giving the whole list to one thread. And this is going to handle the boundary conditions. This is going to be, because remember, we have ghost zones at the end and beginning of the noodle because we need to copy over the values from the other side. And so here we're going to set the very first value to the very last value and vice versa, right? So readable size -2, that's the last real value, and readable size -1, that's the ghost zone reflecting the first real value, right? Because if you look at this thing again, right, this is n-1, that's the ghost zone. This is n-2, the last real value. And here we just have some logic for printing out stuff to a file, for plotting it. Don't worry about that. And then after this run partition has completed, we do another then accept. And here we're just swapping the two lists around, right? So remember, we have an array list of those two part lists, and we just want to swap them because the next time step, we want to read from the list that we just wrote to and write to the list that contains two time steps ago, because we're only keeping two time steps in memory at a time, the one we want to evolve and the one that we're storing the result in. And then after we've done that swapping, we complete the future that we constructed up here, which then in turn tells marching 4 to advance to the next iteration of the loop. And if we run that, oh, you know what? Let me run it over here on our fancy notebook server, which I'll introduce you to in a couple moments here. Has anyone here used Jupyter Notebooks before? Yeah? Okay, so basically what Jupyter Notebooks are, they're just a little interactive environment where you can write Python code in these little cells and run them and have some interactive results. And we've sort of hacked on this to let you run Java and some other kinds of code that you'll see soon. So I'm gonna just say the magic words. Now we can run Java code. $Java. Just paste the heat equation in there. Yeah, I have to give this code a bit of a haircut. And then, if all goes well, this will compile my code for me and run it. And there you can see all the time steps. And now, if we go back to the home page, we can actually see this logic. I remember I told you we had logic for outputting the results to a file. Now we can actually see the results that we computed. I think this is yeah, so at time step 9600, these are all of the grid points. And you can see they're getting smaller as we go further to the right, and then smaller again as we go all the way to the left. In the middle, they're largest because the initial shape was a Gaussian. And then over time, what we should see is the Gaussian is going to be really tall and thin, and it's going to flatten out. So if we look at, it might be hard to see. It would be good if I had a plot. It might be hard to read this
We
way,
could make a plot.
but if you just look at an earlier time step, you can see the values at the extremities are smaller, whereas the values in the middle are a little larger than they were over here. But a plot would make this more clear. I just don't have one on hand for you.
Fast with Matplotlib, but let's not try.
You have your laptop there. I guess you could work on it.
Yeah.
Anyway,
You have the secret word.
hmm?
You have the secret word
The secret word.
for the server.
Oh, let me find it. Coppery hatch 0.
Yeah.
Well, it's a secret that I'm sharing with you all because I value your ability to keep secrets. I trust that this special phrase will not leave this room. Well, I can reset it. Yeah.
Value is like, mostly like, hey, there's a deeper notebook server that's got the password.
Yes, if you texted someone right now and told them to kick us off the internet with a DDoS, then it would work. So don't do that, please. Anyway,
Show them the location of the server and help them get accounts out.
well, first I wanted to ask first if we had any questions about the heat equation code. Yeah. Yeah.
I guess it's really interesting. I'm still having trouble actually understanding the code as in like, why are we swapping the lists?
So basically, we only care about the time step that we have now and the one that we're trying to get to, right?
Okay.
So the way that the code is constructed, it always reads from the first list in the array and writes to the second list. We could have it so that every other time step, it reads from the left one, and then on the other time steps, it reads from the right one. But the way we have implemented it, instead of doing that, it just swaps them. You're just swapping pointers. You're not actually moving data around. You're just saying now, you can imagine the array list at 0 is the source list, and the one on the right is the destination list, and you just swap the two around. Yeah. Okay. So, right. So what the data looks like is this, right? So here's what the array looks like. Everything but the extremities is just normal, right? But on the very leftmost cell here, we have a copy of the value of the rightmost real value, right? And then on the all the way on the right, we have a copy of the leftmost real value, right? And then after we evolve one time step, which just involves scanning through the array and running that computation on every cell, after we do that, we just copy over whatever it ends up here in 9, we just copy it over here. And whatever ends up here in 0, we just copy it over here. And that way, when we run the next time step, we can just read this fake 9 value as if we can access this, right? Because to compute this at the next time step, we need the left neighbor. Does that make sense? Well, copying it is updating it, right? So we're evolving all of these in time, and then evolving the ghost zones in time just means grabbing the value where it really is and copying it over. Yeah.
So is that what we have there in the bottom? Is that counted as one ghost zone?
Yeah. So in guards parlance, it's one ghost zone because there's one ghost zone on each side. It has to be a symmetrical thing. So
And the code, you got to input the amount of ghost zones, right? Is it for one?
yeah. So the second argument's run partition. Sorry. Go ahead.
What happens if you do more?
More than one?
Yeah.
Well, it just means you have more than one ghost zone. So if you have a higher order stencil, meaning you're doing a more complicated evolution, there are a lot of problems where Euler's method isn't good enough and you get instability. So if you're using Runge-Kutta 4, for example, which is just like Euler's method but more complicated, you need more neighbors and you need more previous time steps. Which one was first?
Put back down, like, the entire thing.
Okay. I guess I'll pick you because I pity your tiredness.
So I'm guessing the guards, are those being used at the ghost zone? So everything else is just running parallel without synchronization except for the ghost zones?
So in this case, all of the synchronization is happening within part list. It actually takes care of it for you.
That's like, where is that?
So yeah, so the way it works is because the source list is only being read from and not written to, and we're only writing to a different list. Uh, all of the threads can actually access this list freely while this operation is happening. So the thing we're synchronizing on is we're saying we don't want another thread to come in and then say, I want to write to some section of this list because currently we're locking it for being for reading. So you can imagine part list as a very as a read-write guard generalized to a whole list, right? So instead of synchronizing on single values, we're synchronizing over ranges of values. We can look at we're going to look at part lists more in the future, but we can also touch on it now if you think that would be a good use of time.
Are to theory right? Or is I think I'm forward?
Well, so in this case, we're giving it a number of chunks. So it's actually going to divide the entire array into those two pieces, right? So internally, part list knows that some thread is reading from the left part and a different thread is reading from the right part, right? And until those threads release those particular ranges, nothing else can come in and write to it, but something else could come in and read from it. Does that make sense? I can show you the run part, I can show you the run part of code, or maybe I can't. It might be generated code.
Yeah, it might be a little much.
Yeah, okay. We're gonna talk more about part list soon. Just hang in there. Yes.
What's the important thing about guards is, like, what do we really need to know about it?
Everything.
Specific, like.
Everything we've said.
He's gonna ask you to give you the.
Yeah, that's and I'm choosing not to do that.
So in general, right, we don't want to know the properties of the guards, right? We talked about the properties of that we had. You remember what some of them were?
Yes. It's lock free.
Well, it's weight free. It's weight free to keep and queue something, right? And in fact, it's just two atomic operations to do it, right?
Mhm.
And you can't deadlock with it, right?
Right.
Right. So and it's composable,
Mhm.
right? Those are the kinds of things, and it's asynchronous, right? Those are the kinds of things that you should know in general. And how you run that, how that single guard works, which we spent like 3 times walking through that, you should understand that.
I've got that.
All right.
Okay, so everyone with your laptops, you should visit this link. It's flower.cct.lsu.edu.
I'm gonna put that on the Discord server. And we'll take no more than 5 minutes to do this because we got to get to the quiz.
Yeah. So you must register an account on this server, and to do that, you will need this code right here, coppery hatch 0. And the reason you need to do this is because your homeworks will be on this. The next couple of homeworks will be on this server.
There you go. Link is on the Discord. You know, I accidentally only printed out 5 quizzes.
Wow. Well, we have 5 people.
I would be in trouble if if everybody had been here.
And do anything else like that?
Nope, you're good after that.
We'll tell you what to do with it next time.
What is flowers? Is it a programming language?
Yes. Originally, this was a server for the Flower programming language, and now it's a server for, I won't spoil a surprise, but we have a programming language we're going to learn about starting next time.
All right, you want to put stuff away?
Can we leave it out? I guess we're gonna put it back.
Well, yes, I was just asking politely. But if you make